Hello everyone, let's talk about this question. We're said that we're given a table of n rows and n columns, and the cell located at the intersection of ith row and ith column contains the number I times j. The rows and the columns numbered starting 1. We are given an integer x. Our task is to count the number of cells in a table that contain the number x. Our inputs are n, which is the size of the table, and x, which is the number that we're trying to find the answer for. Let's actually go through one of the examples to see what we mean. Let's consider this example, 6 and 12. Let's go here. As you can see, I already have the table here for the 6 and 12 number. In this case, 6 is the size of the table and 12 is the number that we're trying to find for. As you can see in this table, we can find 12 using 6 times 2, 2 times 6, 4 times 3, and 3 times 4. And because of this, we were expecting the answer here to be 4, and we got 4 different possibilities of getting 12 in a 6 by 6 table. That is all we have to find, but the problem here is, or our challenge here is to do it fairly efficiently. As you can probably see, we do have an O of n square solution here, where we can go through each of the numbers and calculate each of them and essentially increment whenever we find our target number, which in this case would be 12. But as you can also already guess, that would be too expensive since that is an O of n square solution. The O of n solution here, let's look at that. O of n solution would look something like this. In the O of n square solution, this is how it's going to look. We will run through the size of the table. For in this case, that would be 6, because this is 6 times 6 table. Once we have done that, we will find numbers that divide 12 in this case, or our target number. Once we have done that, we can, let's say, call this number A. Once we have done that, we will simply check if 12 mod A is less than or equal to 6 in this case, because we want to make sure that all of the numbers that we are checking occur inside the 6 times 6 table. Once we have done that, we will increment count and simply return it. That is the O of n solution. You can see the code that I wrote here. This is the O of n solution, but there is an even better way to solve this using number theory. Let me show that to you. Let's think about an example. Let's say we were given a table of size 6 and we wanted to find the number of ways we can figure out the number 36. One way is 136, or rather 1 comma 36. Another would be 2 comma 18. The next would be 3 comma 12, 4 comma 9, 6 comma 6. If we have gone through all of these, you'll see that the answer starts to look similar. So when we go to the next one, we will have 6 comma 6 if we want to count it twice, which we should not. But then we find 9 comma 4, 12 comma 3, 18 comma 2, and then lastly 36 comma 1. So to reduce the number of numbers that we have to go through in our solution, we can simply go through these 6 values and still find all of the answers, because when we would have gone through all of these 6 values, all we had to do was to switch the numbers. For example, this 4 9 becomes 9 4, and we would still have our answer. According to number theory, theory, we simply have to go through the list square root of n times. That reduces our time complexity from O of n to now O of square root of n, which is a faster way to solve this, and that is essentially the idea behind this code. We will go through all of the numbers from 1 to square root of n, and wherever we find a number that divides our target number, we will increment our value and keep track of that value. Let's now look at the code. I will start off with my template. I will input long n and x, n being the size of the table and x being our target value. The next thing we will initialize is our count, long count, which I will initialize to 0 at this point. Once we have done that, we will simply run through our numbers, but rather than running through all of those numbers, we'll do I equals 1 and I times I is less than or equal to x. This part of the code essentially makes the for loop run square root of n times. When we have done that, we will check if x mod I is 0. If it is 0, we will initialize another variable, we'll call it j, which will be x divided by I. We're initializing this in variable j just to check if j still occurs inside the size of our table. After that, we will check if I is less than or equal to n and j is less than or equal to n. If they are, we will increase count once. That is basically it for this question, except for one major, I would say, edge case where both I and j are equal. When they're both equal, we do not want to count them twice. So in order to do that, we will run an if statement again, where we will simply check if I is not equal to j and j is less than n and I is less than n. If that is the case, we will increase the count again. Once all of that is done, all that is remaining is to see out our count, and this code works. That was the idea behind this question, using number theory to decrease our time complexity from O of n squared to O of n and finally to O of square root of n, which is, I think, the most optimal solution in this case. But if you can find a better way to solve this, please let me know in the comments as well. Thank you so much for watching this video. I'll see you in the next one.